Hi everyone, welcome to my YouTube channel, My name is Tigana, as you know it. And one more time today, I'm gonna speak in English because the exercise I'm going to solve is the exercise I'm going to solve is um, made for English-speaking people who want some help. Uh, so this is what I'm gonna do. But then let us go directly the exercise and see what is gonna happen. So in this exercise, we're gonna solve a question on of complex analysis. Complex analysis. So the question is stated like this: we have a function. We are given a function small f, whose domain is called here f, and a part of the complex set, which is a C, and which also had text value in C, and we assume that the here when we write f like this, it means that u is the real part of f and the v is the imaginary part of f. So it means what? What does it mean? It means that if I want to compute u of z, I can see it at u of x, y plus I, v of x and y. Here then, z is seen as x plus I, y. So because all the complex numbers are written like in this form, that's why we prefer it usually. So then if you define w of r to be this one form, it means u dx minus v dy, and you define wi to be this one form, v dx plus u dy. So we have two one forms. We define them. Then the question asks us to prove that f has a primitive if and only if these two, one form WR and WI, are exact. What does it mean that in one form is exact? For WR, it means that we can find a C1 function that we call here capital U such that d of that C1 form is equal to WR, and for WI it also means that we can find a C1 function that we can call capital V such that dV is equal to WI, and this is now what we have to prove. But when we are done proving this if and only if condition, the exercise is also showing us that the primitive of f, or small f that we're talking about, if we call it capital F, it is going to be nothing else but this. F is going to be u plus iv. It means that if I want to compute f of small z, z seen as x plus I, y, it's going to be nothing but u of x, y plus capital V of I, capital V of x, y. So this is what we're gonna do. So here you see we have an if and only if problem to prove. We must prove that f had a primitive if and only if WR and WI are exact. It means that we have two things to do. We're gonna prove the if and then the only condition, the if and then the only condition. The if condition, it means that we must assume what is on the left side of if and only if. We assume it and we see if we're gonna get what is on the right side. And the only if condition is gonna be that we assume what is on the right side and we see if we're gonna get what is written in the on the left side. So that's what we're gonna do. So let us start the solution. So we're gonna start with the if condition. The if condition, we assume that f has a primitive. So if you assume that small f has its primitive and you call that primitive f, we know that this primitive, what does it mean that small f as capital F as a primitive means that the derivative of capital F is equal to small f. So then let us define capital U to be the real part of capital F and capital V to be the imaginary part of capital F. We know that the derivative of a complex function can be written like this as the derivative or the derivative of a complex function at any point x or z is what is the limit as z goes. So let me write h goes to 0, f of z plus h minus f of z, capital F of z, divided by h. Now, if we assume that the derivative of f, capital F, exists and is equal to small f, this limit always has a limit. The limit is this, always a limit. But look, we can assume, for example, that our h that only has our h only has like real part, no imaginary part. Then here it is like we fix the so here in the difference is z plus h minus f of z. What is happening here is that we're computing f of, for example, x plus t plus I y, y is fixed, minus f of x plus I y, we divide by t. So you see that here, when we will write f in the form of u of x plus t y plus I v of x plus t y, and we do the same thing minus here with u of x y minus I v of x y minus I v of x y. So we divide everything by t. So what are you going to get? You're going to get here that you have v u of x plus t y minus u of x y divided by t plus I v of x plus t y minus v of x y divided by t. You see that this limit as t goes to 0 is going to be the derivative of f at z, because the derivative exists. But as t goes to 0, this gives you the partial derivative of u with respect to x, plus as t goes to 0, this gives you the partial derivative of v with respect to x. So that's why you see that here we write f prime is the same as this and is also the same as this y. In the other case, we can also assume that h doesn't have any real part. H is just this. So if we write h like this, you will see that in the difference, we will have in contrast to what we did. So z plus h is going only to be x plus y plus t I. So then what we're going to have here, when we will do the difference, we are going to have the same thing here, except that here we have I, and there we also have I. But it will shift now then. So we'll shift like, oh no, so let me write it properly. So if you write it properly, we're gonna get something like oh my god, shit. It's not going. I want this to go. Okay. Now, if we write it properly, we're gonna get like something like x y plus t minus v of u of x y divided by I t plus, right, v x y plus t minus v, capital V, x y divided by I t, and there's an I here. You see that there we can cancel these two I, but here this I will come there, and then that will give us the real part will shift, and this I will come with a minus sign. That's why we have this part. We have then Vy, the partial derivative of v with respect to y, minus I, partial derivative of u with respect to this is the derivative of f. This the derivative of f with respect to z in general. Now, what does it mean that f is equal to? Because we know this f capital F derivative of capital F is equal to f, and f is written as capital F is written like the derivative of capital F is all this, and the f also is assumed to be small v plus I small u plus I small v. So we can write this for for in the case that v is written like the derivative of capital F is this. We can also write this if we consider the derivative of capital F like as this. And from those two, from this, we have that u equal to, small u is equal to the partial derivative with respect to x of capital U, and also small u is equal to the partial derivative with respect to y of capital V. So this gives us the first two equations. We can also see that small v is equal to the partial derivative of capital V with respect to x, and small v is equal to minus partial derivative with respect to y of capital U, which gives us the second set of equations. But then, if I compute, now let us compute du with all the information that we have, because our aim was to prove that we can find u such that d of u is equal to the omega r, and we can find v such that d of v is equal to omega I. So we have found already a u like this and v like this. We want to see if they are the one we were looking for. Then we have to compute d of u and the d of v and see if they are going to fulfill these conditions. So then let us see. D of u is what? D of u is ux dx plus capital Uy dy. But we've seen from the first equations that ux is equal to u. Capital Ux is equal to u, small u. And capital Uy here is equal to minus small v. So then all this is u small u dx minus small v dy, which is the definition of WR. So this condition is satisfied. Let us compute then dv. dv is equal to d capital V. D capital V is equal to capital Vx dx plus capital Vy dy. But capital Vx, we've seen that it is V. So we can write it as small v. And capital Vy, we've seen that it is small u. So we can write it here. So we have this, which is the definition of Wi. So it means that the d of capital V also satisfies the second equation that we were looking for. So we done for the if proof. Then we go to the only if condition. in the only if condition. Now we have to assume that WR and WI are exact. So we assume WR. That means if a one form is exact, it means that for WR you can find this capital U, and for WIV you can find this capital V, that those are which are C1 function error 2, such that D of U is capital U is WR and D of capital V is WI. So then we have to see from this equation, this is WR, which is this, but it is equal to D of U, where this D of U or D of U is the partial derivative of U with respect to X, dx plus the partial derivative. So this is what we write here as ux dx plus uy dyu. This is D of U. But from this equality, we can conclude these equations that U, small u is the partial derivative of capital U with respect to X, and small v is the partial derivative of, is negative the partial derivative of capital U with respect to Y. Also from this equation, we have that this is WI, which is this, and must be equal to D of V, but D of V is V, small capital V X dx plus capital V Y dy. From this equality, we can conclude that small v must be equal to the partial derivative of capital V with respect to X, and small u must be equal to the partial derivative of capital V with respect to Y. Likewise, but then here this is small u, this is also small u, then they are equal. This and these are equal. So capital U with respect to X is equal to capital V with respect to Y. And look, this is small v, this is also small v. That means that capital U Y is minus capital V X. This is what we call, this is the Cauchy-Riemann. If we define then V to be equal to this capital F to be equal to U plus IV, then from these equations we can conclude that this function, complex function capital F, satisfies the Cauchy-Riemann equation, which means that this capital F is a derivable function, is derivable, and the derivative of capital F is what is, as we have seen it, is partial derivative of U with respect to X plus I, the partial derivative of U with respect to X. Then we can come back to this to see that the partial derivative of U with respect to X is equal to small u. Then you can write it here, and the partial derivative of capital V with respect to X is equal to small v. We can write it there. But when you write like that, we get F, a function F. That is, F is a primitive of small f, and in that case we have seen that always the primitive is written like this. And then from here we conclude the proof of our exercise. And I can also ask people who are following, don't forget, always share with people you know they speak English, because we want them to subscribe to our channel. We want them to subscribe to our channel to continue to follow, because this channel is not the one who's teaching mathematics in English or French. I'm teaching mathematics in Lingala, my local language. It's this channel, and I want them to subscribe, because I think that it is very important that we start as African, we start also being capable of teaching, of transmitting the knowledge that we have in our local language. This will do two things. It will enrich our languages, and it will maybe help us to master, to understand well what we're learning, and to understand well how to use the knowledge that we are learning in developing our own spaces. So that's why I beg you to share and to share to this video with people that you know they speak Lingala, they are from DRC or from